Hello, I'm Weili Fu. I will present Provenance of Configuration Language muPuppet. This is a joint work with Paul Anderson and James Cheney. Computing systems become more sophisticated due to the increasing numbers and kinds of machines and the complexity of the softwares. This makes configuration tasks very demanding. With this requirement, automatic configuration management tools have been developed. These tools including their own languages. Those languages are typically declarative. However, these tools have their own weakness besides the benefit. Their implementations lack of formalization behind. This arises security concerns. There's no guarantee of correctness of generated configurations. The configuration generated by those tools do not necessarily meet the requirement. There's no means to detect and correct errors if configuration failure happens. There's no means to understand configurations. We don't know where the input data are from and whether they are reliable. Let's look closely what configuration language do. Their purpose is different from general purpose programming languages. Their purpose is to describe many parameters and relations among them, instead of realizing functionalities. The specifications written in those languages are from many contributors. This arises particular security requirements. We want to guarantee the correctness of the input data in the configurations. We want to understand the source of the data, so to blame the right contributors if there are errors. Access control is a desired security feature due to the many contributors. The solution to improve the security of configuration language is provenance. This is a technique invented in database field. It's to record the history of evolution or lineage of data in databases to audit the integrity of data. Databases are under ever-changing. It is crucial to know how the new data is generated. There has been few models proposed. Where provenance is to record all the data that contribute to one output data. Why provenance is to provide different explanations to one output, because one new data in database can be generated in many ways. How provenance tell you how the output has been computed. Provenance in general is a metadata formalized in the general way as follows. The data in the database are annotated by labels first, and those annotations will be propagated or involved over query evaluation. And the result annotations on the input are the provenance information. There are other developments using provenance technique as well. Dependency provenance was proposed to track information flow in the computation for program analysis. To realize provenance technique in the context of configuration language, there are two steps to do. First step is to formalize configuration language. We chose Puppet. It is a popular commercial configuration tool. It includes its own language, Puppet language. Puppet language is mostly declarative language, but is implemented in ad hoc style. We explored a core subset of Puppet language and its semantics. We formalized the semantic of the core subset by using operational semantic from program language theory field. The formalized core subset is muPuppet language. Then the second step is to build provenance models. The provenance models will be built on the operational semantic of muPuppet. We'll establish three models. They are where provenance, expression provenance, and dependent provenance for different aspects of information of data. Before I get into the formalization of provenance models, Let's look at 3 examples of these 3 models. In this example, we see the program in Puppet language and the compilation result. In the program, we labeled all the input value or the row value in the program. And in the compiled result, we see the labels are copied from the input. There are some labels disappearing. This is because how we define where provenance for. It is the information to only record the input value that didn't take into any computation or primitive computation in the compilation stage. So if any input take part into any computation, so the input and its label will disappear in the result, also in where provenance. And with where provenance, we can also differentiate where this value is from exactly. We see the value 123. There's 2 variables have this value. And in the result, the value of mode is equal to 123. It's labeled by L2. And by the label, we know this value is from the value of top arc instead of the argument node arc. For expression provenance, we do the same. We labeled all the input value in the program and in the compilation result. And we see the label of 223 is labeled by a formula. This formula record or represent the computation that resolve this output. And with it, we also know all the input that join the computation. And for dependency provenance, the result is to record all the input value that could influence one output value that take conditional statement into account. In the program, we see there's an if statement, and the result of the mode variable depends on the value of the conditional in the if statement as equal to true. And beside 2 other value in the program. So the label of 123 in the result will be a set of label that's corresponding to all the input that could influence this output. To model provenance, there are 2 aspects, syntax and semantic. As we see in the example, the syntax of provenance are just annotations on muPuppet syntax. The semantic is generated by the propagation of annotation through compiling procedure. The reduced annotation on the input or output data are provenance information. The annotations are propagated in different way for different provenance model, as we saw. That means different provenance model have different semantics. Let's look at the formalization of provenance models. In where provenance, its annotation is either a single label L or a bottom. And we use plus operation as an example. These 3 rules are written in operational semantic. The first rule says, if the 2 operands of the plus operation are expressions, we will evaluate the left operand first. The second rule says, if the left operand is a value, we'll evaluate the right operand. The last rule says, if both operands are values, the result value will be labeled by a bottom. That's explain the meaning of where provenance. In the result, we only record input that didn't take part into any primitive computation. In expression provenance, the annotation is either a label or the annotations corresponding to the primitive computation in the language. For example, plus, minus, or comparison operations, and so on. In the plus operation, the result of the plus operation will be labeled by the two input label with the operation plus. In dependency provenance, its annotation is a set of labels. And for plus operation, the result of plus will be labeled by the label of two input, by the union of the label of two input. Let's see another example in this Puppet language, the selector expression. This expression is a conditional expression. And in the rule as truth, it says when the branch under consideration matches the conditionals, then the result expression will be labeled by the union of the labels of two conditionals. And the last rule says when the current branch does not match with the conditionals, the result expression will be still labeled by the union of the label of two conditionals. This means whatever the current branch matches the conditional or not, the resolved expression will depends on this current branch. Besides the syntax and semantic prominence models, we also need to define the correctness to test whether our definition meets our desired. That's how we have this following lemmas, following theorems. For the correctness of where provenance, we define in the following way. We require the set of all labeled output is a subset of the all labeled input values. The label functions is to subtract the labeled values from the program. For the correctness of expression provenance, we use a consistency relation to define. Let's see the mu function first. This function relates labels and its values. We know that all the values in the up program are labeled uniquely, so we can build such mu function. With mu function, we define consistency relation as follows. This relation relates the input value and its label first. And when the input value take part into any computation, the result value will be related to the result annotation that's responding to the operation. So with this consistency relation, we state the correctness of expression provenance as if the program satisfies consistency relation, the compiled results still satisfy this relation. For the correctness of dependency provenance, we need to describe observation. That is, if we change a value in the program, we want to know for some particular output if it's changed or not. With this observation, we can catch or test if the dependency provenance generated are correct or not. For this purpose, we define floor relation and equivalence relation. Floor relation just ignore or omit the value labeled by a set of labels that's including the label in the consideration or in testing. So we leave this value as a whole. So with this relation, we can define equivalence relation on two programs. That says two programs are equal if it satisfies the rules. That means with one label under consideration, these two functions are the same. With this equivalence relation, we can test the correctness of dependency provenance by we take a label in the provenance in consideration or for testing, and then we will change the input that labeled by this label and see if this output labeled by this label is changed. In this way, we can test whether the dependency provenance is correct or not. However, this correctness does not cover all the program in muPuppet. There is an example. In this program, a class is defined and then declared. And for the value of W, it depends on the parameters X. And when X is equal to 2, the value of W is equal to Y equal to 1. And in the case X equal to 1, and then the conditionals in the definition will be executed, then the value of W is equal to Y and equal to 42. And when, in this case, X equal to 2, and in all dependence provenance model, we didn't catch the dependency that X equal to 1. Actually, the result of W relies on X equal to 1, no matter the real value of X as parameter is. So for this reason, we narrow down our correctness conclusion for those Puppet programs exclude such programs. Conclusion, we propose to use provenance technique to improve the security of configuration languages. We defined 3 models and established the correctness semantic of those models and prove their correctness or partial correctness. In the future work, we'll prove the correctness of dependency provenance on full muPuppet. We'll implement these 3 models in Haskell. We have already implemented muPuppet in Haskell. We can also extend muPuppet with more language features and extend provenance models to them. We can also explore more provenance models for security features, such as secure access control. Thank you very much.